so let's talk about the arc length. As you may recall from Calc 2, the expression for two-dimensional arc lengths were this, right? Now that we have 3 dimensions, we got to add in a change in z as well, okay? But the good news is now that we know about vector-valued functions, we can write this expression a lot more concisely, okay? So now all this is saying is r of t is your position vector. We're going to derive it, so get our velocity vector, and then take the magnitude of that, and in turn get this, and integrate it from whatever, over whatever your interval is, okay? So let's go ahead and do a quick example just to see how this plays out. So we got r of t is sine 3t, cosine 3t, and 6t. We're going from t equals 0 to 6, okay? So first thing I'm going to do is I'm going to find my r prime. Well, that's just going to be 3 cosine 3t minus 3 sine 3t and 6. Okay? Then I'm going to find the magnitude of my velocity vector, or the derivative of my position vector. So this guy. Well, that's just going to be square root of 3 cosine 3t all squared, which is just 9 cosine 3t squared, plus 9 sine squared 3t plus 36, right? So now what I can do is factor out the 9. I'm going to get a cosine squared t plus sine squared t, and then outside the parentheses plus 36. This is just 1. So now all I have is a 9 plus 36, which is just root 45. So now that's my the magnitude of my velocity vector. So what I'm going to do is actually put it inside the integral. So I'm going to go from 0 to 6. Those are my bounds. And I'm going to integrate this expression, right? Now, it just so happens that in our case, this expression is just a constant, which is just root 45. We're integrating from 0 to 6. Well, that's just integrating a constant. Just pull it out, and you get just 6 as a constant multiple of root 45. So that is your answer, okay? So finding the arc length in 3 dimensions, just like in 2 dimensions, except now we can take advantage of vector-valued functions, and now we have a sort of a different looking formula, but in turn it's saying the same thing. The calculation is still the same, except when we depict it, it's a little neater and cleaner. So there you have it.